Okay, everybody, thank you for coming to the UCLA Meteorite Gallery Lecture Series. We're pleased that you guys could come in. Today, we're pleased to have Laurence Garvie from ASU. I asked him for his bio earlier, and he said, and I quote here, "I am the curator for the Busick Center for Meteorite Studies and research professor in the School of Earth and Space Exploration. I am primarily a mineralogist and have a keen interest in minerals from meteorites as well as odd terrestrial environments." Now that's the end of the quotation. I'll continue out. He got his undergraduate degree in math and earth sciences at University of London, a PhD in clay mineralogy, looking at tiny stuff, giving him a good preparation for looking at carbonaceous chondrites from the University of Bristol. He did a postdoc in electron microscopy at Glasgow, where we were all last summer. Came to ASU way back in 1994 and joined the Center for Meteorite Studies in 2007. He said his favorite activity of all is to cut open new meteorites and see what is inside. Anyway, the title of his talk today, which I will give a truncated version of the title, is The Fall, Recovery, and Scientific Analysis of a New LL7 Ordinary Chondrite, the 2016 Arizona Meteorite Fall. This is the most recent United States fall that's listed in the Meteoritical Bulletin, but there are more that are on the way. Anyway, I'm pleased to have Laurence here. We have a little bit of background noise, which I think just dissipated. And but okay, well, thank you, Laurence. Everybody should go now on mute except Laurence. And please continue.
Okay, thank you. Let me just share my screen. Thank you, Alan, for that introduction. The screen showing, thumbs up from somebody. Okay, let me just go on to here. Well, you know, I'm just going to give a more of a sort of a general talk about finding a meteorite and basically try to convey some of the excitement of finding a meteorite. And this was something that happened here, sort of in our back garden, so to speak. And so there's the title, the name. The actual official name of the meteorite, if you look at the Meteoritical Bulletin, is Dishchii'bikoh. It's the first part. But the full name, and we can talk a little bit more about that afterwards, it's called Ts'iłsŏօsé Tsee, so Dishchii'bikoh Ts'iłsŏօsé, which means Dishchii'bikoh starstone. But we can talk a little bit more about that, or Ts'i'bikoh starstone, later on in the talk. But before I really sort of get into the talk, what I want to do, I put this slide in here just very quickly before we start the talk. Recent falls, it's been a very busy year so far. We have the January 20th Oklahoma fall. I have a slice, one of many slices, one of the slices here. And actually be classifying it. I'm on the probe tomorrow morning, so I'll be classifying that. There was another, I have to say, still secret fall in late January, which is quite an interesting one. And then just in the last few days, 3 more falls on the 13th in France. These are recovered, not just somebody saw a fireball. These actually, all of these are recovered. So France on the 13th, Italy on the 14th, and Texas on the 15th. So it's been quite an exciting time so far for these falls. And basically, us as collected scientists and collectors alike, we all really benefit from this. So let's get back to and that was just an aside, just to say it's been a very active year so far. You know, an introduction, just I want to talk about the fall and the meteor and the collection of the meteorite, what was involved. And this is something was the first, I mean, I had found meteorites before this particular example, but they were more cold finds, just hiking around in the desert. This was the first time I actually went to look for a fall, which was very exciting. And I'll show some photos of that, a little bit what's involved in classification, and then 1 or 2 slides about the science and basically the ongoing science of this. You know, why are we studying it? What's it telling us? You know, this really started, it was early one morning. I just wakened up, and one of the meteorite dealers I know, Mike Farmer, sent me this text. It was the first, I read the text in the morning, and I immediately knew this was going to be an extremely busy day at work. In fact, turned out to be an extremely busy few days at work. And I knew as soon as I got to work, I'd be barraged or inundated with media calls. And absolutely, I got to work around 9 a.m. and the media crews were already waiting. And my phone was ringing, and I had emails from various outlets and organizations saying, what is it? How much has fallen? What do you think fell? And of course, this was early in the morning. We knew almost nothing, except we had radar reports. We had lots of videos of the fireball. This was the text that I got in the morning from farmer. And then basically everything then evolved from here. So we also knew from the American Meteor Society Fireball report that this was widely reported and widely heard here in Arizona. And I think various people from ASU also saw this as well. So it was seen east of the valley. And, you know, we knew from the numbers of reports that there were likely stones on the ground. But then obviously the question is where, you know, where to start looking. We were extremely lucky to also have radar. So here's I put here the trajectory of, I think I'll get this out of the way. I put here the trajectory of what was seen based on the video reports. So we knew basic where sort of the direction it came in, the height that was first seen in the atmosphere, and the direction that it was traveling. The 3 stars that I see here at 25, 29, and 34 kilometers were the major flares in the fireball. And then by just under 25 kilometers is where it was last seen before it went into dark flight. And then we also have, see in the box below, by the way, Payson, for those of you who don't know, is about an hour and a half, 2-hour drive northeast of Phoenix area here. So it's in a really remote and mountainous part of eastern Arizona. So we'll see some photographs of that in a minute. Very, very difficult area to get to. Now, the color in the square box on the bottom, and we'll look at higher magnification in a minute, is actually the blue are radar returns, Doppler radar returns, and then the colored, going from yellow down to red, is the projected, based on the radar returns and the incoming fireball information, is where we expect a strewn field to be, if anything at this stage is on the ground. If we look here, this is the Doppler radar returns, and several radar sweeps actually showed a progression of, in fact, they showed several things. They showed a progression of a cloud of smaller materials, and then in several of the returns, a larger single return of a larger object. But then when we actually, and what's really nice here was that we were very fortunate at this time as well, is that the incoming fireball occurred on a clear morning, very low upper level winds, no storms, very, very good visibility. So we were expecting that the radar returns, which are then projected down onto the ground, are telling us where we're likely to find stones. In this particular case, though, we were both fortunate, one second, and unfortunate, because the radar returns are over tribal lands. This is actually occurred right over the White Mountain Apache tribal lands. And that meant 2 things, actually. It meant that the non-native tribal people can't go out there and search. So basically, we couldn't have meteorite dealers going out there and just searching. It also meant that we couldn't go out there and search either. So it was a sort of a difficult situation. It was like, well, there's almost certainly meteorites on the ground, but we can't go and search for them. By the way, guys, can you guys see this? I'm trying to hide this. Let me hide this down here. A second. There we are. Sorry, I'm just trying to hide that screen. So this meant that we couldn't actually go out there either. So, you know, when we looked at the Doppler radar returns in more detail, it shows where the meteorites are likely to be based on the radar returns, and also gave us a good indication of where we might go and look. But there's really no roads in this area. It's very, very mountainous. And as I said, it's on the White Mountain Apache tribal land. Down the bottom right, you can see the only main road in this area, which is a 2 to 4 lane road that passes through the tribal lands, and you know, a good tens of kilometers away from where we were going to search, or where we wanted to search. So the first thing we needed to do was actually try and get permission to go on the land. And I was fortunate, and we have some tribal representatives here at ASU, and I contacted them and said, is there any way we can get onto the land to search? There were several things. This was midsummer, so obviously we had temperatures of 100 and teens in the valley, so that was not particularly easy. There were wildfires up in this area, up in the forested regions of this area as well. And So this made it particularly difficult to try to get access to this region. So fortunately, our tribal representative here contacted the chairman at this particular case. Was a chairman who was in charge of this region. Said, you know, is there any way we can get up there? And also, time was not on our side as well, because you know, usually by mid to late summer, our summer monsoons come in and dump several inches of rain, which would make this area virtually, if not impossible, to get to. So we knew we were on a time crunch as well to try to get access to this location. And there was also no guarantee that we were going to get access at all. But after literally a frantic week of sort of emails and collaborations and discussions, we had their chairman and the president of ASU giving us basically agreement and access to this area. So in this case, put up at the top, Jacob Moore, the ASU Assistant Vice President for Tribal Relations, negotiated. We signed a formal legal document that gave us right of access. Didn't give us permission yet it gave us permission to look, and if we found anything, to collect anything, but it still didn't give us access or rights to do anything else if we found anything. So this was very fortunate. So again, this was all happening very rapidly. And then also to get a team of people together to go and search this site as well. So I think we were given like a week. So we were told to meet at where the paved road ends in the town of Ts'i'bikoh, which is this is the only small inhabited area in this region on the tribal lands. But as we got there, I was actually able to we got a team of 2 grad students who have now graduated and both have good jobs, and 3 meteorite hunters who are very experienced. And we waited where the paved road ends at the end of Ts'i'bikoh, and we're waiting for Ranger Amos. We were actually going to collaborate with some of they have a small college on the tribal lands. We were actually going to collaborate with some of the kids in the tribal college there, but they were also having the large wildfires on the tribal land. So when we got to the edge, when we got to this location, I phoned the Ranger Amos, and said, you know, we're waiting for you guys. And he said, well, sorry, we can't meet with you guys because they were evacuating some of the larger locations, some of the smaller towns to the north of this location. But fortunately, we were really lucky, because I actually thought that at that time we were then not going to get access. We were just going to have to turn around. But he said, look, if you guys know where to go, feel free to go. So we were very, very fortunate. I was very grateful that he allowed us on, even without their escort. They were going to escort us down to the site. It also happened to be, by the way, when I was discussing this with some of the people from the tribal council, that where we were going was the most, as they say, the most religiously conservative part of their tribal lands. It's a land that they don't even go to very often. So again, I still feel very fortunate we were able to go out there. So we went out there. We knew approximately where to go. I think you can just see, I don't know if you can see there's a little dirt road. There's a very, very poor dirt road that actually went through the location we wanted to go. So we knew where, with GPS coordinates, we knew where to go to, and we found a suitable place to camp. And we were, again, as I said, we were given 3 days of access to this site. So we went out and we camped in this location and basically went and searched. This is basically the hunting ground. Beautiful, I mean, really beautiful location for hunting. This is over a mile high. We have sort of, no, there were a few cacti, not many cacti in this particular area, but the hunting ground was what you're seeing here, these reddish rocks. Fortunately, no black rocks in this area, so we were very fortunate. So basically, we were just looking for and just walking under where the radar returns were and looking for any black rocks that we could find in this location. And I found the second stone. Robert Ward was one of he found the first stone within about 5 minutes of looking. And then while he was recording the location of his find, I then started to look around, and I found my first stone here as well. This is, and you can see how lucky I was. We have the oak leaves around the outside, a small patch of bare ground, and fortunately, it was the only black rocks out there. I would say, had this fallen further southwest here, where we have desert varnish, these stones would have been virtually impossible to find. And we know that because we actually have a meteorite fall that occurred just south, about 40 minutes south of where I live, or 40 minutes south of ASU. And people have found a few stones out there, and I've gone to look, but basically you're looking for small black stones on ground covered with small black stones. So they're virtually impossible to find. So we're very fortunate here to find these small patches of ground. And basically the only thing you could do was just walk and look. That's all we could do, just walk and look. This is just a close-up, and it shows how distinct this material it was. You know, people often ask, well, how did you recognize such small stones? And again, fortunately, they were so out of place, you know, that it was, you know, I'm not going to say easy to find because they were relatively few and far between, but they were relatively easy to find because the ground was very conducive to seeing them. This is Daniel Dunlap, who was a grad student at the time. Here's his stone. He actually found it was like 1 gram. And this is, I really commend him on recognizing and actually finding it. It was actually in that clump of grass that his right foot is beside. It was actually just resting in the clump of grass. So that was unfortunately his only find for those few days out there. But he was very fortunate to find that stone. And this is just to give an indication of what this location was really like. This was after near the end of the day of hunting. As I said, it was warm, but being relatively high, not quite as hot as the valley. And here we are looking southwest of where he had just found that 1 stone, trying to figure out where to look next. As you can see, in fact, what's really interesting is that if the southwest where you're looking is where, remember how I said earlier that the radar return indicated or quite clearly showed a distinct return of a larger, at least 4 kilo stone. It's in that direction, somewhere in that direction. And we'll get to that further later. Anyway, so this is just gives an indication of what the location was like when we were searching. I like this one as well. This is Projecta Mane, who was a grad student at the time. She's now obviously graduated. She's found a stone. In fact, I'll just give you a second before I switch to the next slide to see if you can see the stone. Again, you needed really good eyes to see the stones here. The stone, actually, the fragment of the stone is just in front of her. I'll show you up close here. This is looking straight down, and I'll show in the next one what it looked like. And here's in the next one a bit closer. They're the 3 fragments of it. So this was a single stone. You know, they're coming in at dark flight velocity. So what would this be? Something like about 50 miles per hour, maybe 60 miles per hour, something like that. So it's not surprising that it broke upon impact. And there's the close-up of the stone. And actually, behind it, there's a little fragment as well. So she took care to acquire all the fragments from here. Here I said at the bottom, stones in the 1 to 20 gram size range, impact dark flight mode at about 70 to 140 miles per hour. So if they hit a hard stone, not surprisingly, these relatively soft, it's not really the right word, but relatively soft stones tend to break upon impact. The only other things that really made hunting in this area difficult, the wildfires actually brought ash into this area, and the ash in places looked that was lying on the ground from the wildfires looked exactly like the white of the stones on the inside. And the only other things that were round and black that were relatively common were sort of droppings from rabbits and mule deer. And that there was more than once we picked up a dropping from a rabbit because it would look black and shiny and look just like a meteorite. Those were the only other black, round, shiny things in this area. So just, I think, another photo. This is the largest stone that was found, the one I found in this location. Again, see how easy it is to spot from the surrounding materials. And this is then just a map of what we found in this area. The 0.2s and 0.3s is where we wanted to hunt between from the radar returns. The radar returns said this is where the 1 to 10 gram size stones are likely to be. And it shows how good the modeling can be now. This is exactly what we found, pretty much what we found on the ground. And this, I always have to say, this was from 2.5 days of hunting. And there's probably, from the grounds that we covered here, I'm guessing many hundreds of stones in this area. But we got permission just for the few days. So we spent a few days in this location, but then we really wanted, and this was the really high, relatively flat areas that we hunted in. We also wanted to see what it would be like to hunt for the larger radar returns, and that's what we did on the last day and a half, was to go and hunt in that location as well. But as I saw when Daniel was standing there looking south, you saw the difficulty of hunting in that area. And this is what it looks like to the south. So we're standing up high, about 6,000 foot elevation. You can just see in the middle down here, there's a dirt road down there. And that's basically where we were heading, because the Doppler radar return shows it basically, if we're looking southwest here, that's basically where the larger stone or stones are almost certainly on the ground. So we spent the last day or so hunting in this location. But this just shows you, I think, how difficult it is to hunt in this area further to the south, further on the lower. You can, oh, let me go back. You can see here, if you can see right in the middle of the screen is Daniel Dunlap looking over the edge of what is it now, a dry waterfall. And this was one of the flatter areas for hunting. So no, not surprisingly, we did not find the 4+ kilo stone. It's out there. I mean, this is what's so infuriating. It's out there. But hunting it and finding it is going to be virtually impossible. So we spent a day or so and realized that hunting out here is going to be too difficult. So at the end of the 3 days, this was just a collection of what we found. I said the 4 kilo plus stone or stones are still out there. And we could probably gain access. We could probably get access to hunt again. But I think at least for research purposes, what we have in the collection is good enough. And I've tried to work with the tribal people to get them interested in hunting out there and searching for meteorites, but without success so far. I haven't managed to get them to go and hunt. So once we got the stones, then what? So we had to then go through the whole rigmarole again of getting the ASU lawyers involved again and coming up with a legal document which allowed us to curate and study the stones. In other words, cut pieces off and do analyses and work with type specimen masses and so forth, but with the understanding that we are curating them, but the meteorites still belong to the tribal council. So it still belong to the White Mountain Apache tribe. It's just, I just think a beautiful shot of most of the stones that we found at the time. So relatively small, but easy enough for the scientific work that we needed to do. So for the next part of the talk, let's just go briefly through what do we mean by classification. So going from a stone to something that and saying what is the material. So right now, all we know from the interior, obviously the stones are broken. I think you saw from that one photograph where Projector Mana was looking at the broken stone on the ground. It's white and crystalline inside, so we know it's not a dark carbonaceous chondrite. We know it's not an iron meteorite, and there's various things we know that it's not, but it wasn't obvious. It was very coarsely crystalline. That's all we could tell from the hand specimen. No obvious chondrules. So we're not 100% sure at this stage, when we brought it back to the lab, exactly what it was. So obviously we have to take some fragments, embed it in epoxy, polish those fragments, also got a thin section made, look at it under an optical microscope, see if we could see what are the minerals, what are the mineral components, what's the textures, do we see any obvious chondrules, and then like for almost all the meteorite classifications that we do, we then had to go onto a microprobe to get the chemical data, and primarily the chemical data from, in this case, olivines and pyroxenes, and basically what else is interesting in the meteorite. And there were some interesting things in this meteorite. The write-up, which we'll see a bit more in a minute, talks very briefly about, in sort of a quick terms, what do we see, what are its compositions, what are the textures. For the meteoritical bulletin, we're not supposed to put much interpretation. It's mainly sort of observations. So that's what we focus on for this part. And here's one of the was I think the first image we got from the SEM. So we look at the scale at the bottom, 500 microns, so that's 0.5 millimeter. So we see this I think quite interesting set of textures, and there's also, I think, indicates why the stone was so soft and sugary, so to speak. I mean, it had a really sugary texture in the broken fragments. And so we can see near the top of the stone, we see this very, what we'll call a patted plastic, so almost like a crushed and lightly welded together texture. In the very middle, we have a different textural relationship of what looks like a class. On the right, well, we have a different texture. And can we see maybe a relic chondrule here? I sort of convinced myself that sometimes I do and sometimes I don't. So we were fairly sure at this stage that we had a chondrite. That we have here's another area where I think in the middle we see a relic chondrule just here. So we're fairly sure at this stage that we had a chondrite just based on what we're seeing in the backscattered electron images. And then comes the relatively time-consuming part of getting the data. What does the data tell us? What is the chemistry? So for the classification in this particular case, we focus primarily on the minerals, on the primary minerals. In fact, if you look at the backscattered electron images here, we see, what can I see? So if we're excluding the really bright, the white materials, which are metals and sulfides and maybe some chromites, how many levels of gray do we see? I think I see 3. There's the dark gray, which will be the feldspars. There'll be a medium gray, which is likely the pyroxenes, and a lighter gray here, which are likely the olivine grains. So, and there's actually a lighter grain up here, which might be some phosphates as well. So we basically focused on the silicates, which allow us to classify the type of meteorite that we have here and acquire, in this case, I think 10, 20 points from each case. But in this case, it's equilibrated. So all the olivine compositions come out essentially the same composition, same with the pyroxenes. And so, it's a relatively easy meteorite to classify from that point of view. That's the data. And from that, the scientific analysis, what does it look like inside? So we just basically have some, white gray, we see troilite grains, some class, no visible chondrules in the hand specimens, but I think we could see some chondrules in the backscattered electron images in the electron microscope. And then we go to the next level. What do we see inside the microscope? Some remnant chondrules, minerals as we would expect. It's dominated by olivine, pyroxenes, plagioclase, feldspars, and metal and troilite, and then the chemistry. And then the chemistry here tells us what type of, in this case, chondrite is. It's quite high iron content in the olivine. Again, we acquire the manganese, iron oxide to manganese oxide, iron oxide to manganese oxide ratio. So this data then is used to tell us what sort of meteorite we have. We have an ordinary chondrite. The olivine concentration cell is olivine. The olivines say that it's LL. But again, the textures I thought were quite curious. What we're seeing here, we're seeing these areas which just look like they were welded together, sort of high temperature, equilibrated. Then we see these regions where it looks like it's been really crushed, maybe by an impact, but we don't really see many shock effects, especially not in the thin sections for this. We're really we didn't see any obvious shock effects in the olivine grains or the pyroxene grains in thin section. So it was interesting what had happened here. So we have to think of what actually happened to this in the past. And one of the things I was thinking about is maybe this was impacted, but then not re-welded, sort of impacted, but then heated to relatively high temperatures to allow it to be equilibrated. It's something we can discuss and think about afterwards. So the naming of the meteorite in this case was quite interesting because, typically a meteorite is given a name from the location in which it falls. So in California a few years ago, you had one fall at, where gold was first discovered and prompted the gold rush was the Sutter's Mill. It was actually, one of the first stones is actually found in Sutter's Mill, right? But so it was given the name Sutter's Mill. We actually had one fall after Dishchii'bikoh here in the Phoenix area, just northwest of the valley here, but still in the metropolitan Phoenix area called Glendale. Haven't actually had one fall in Phoenix yet either. Glendale is also an interesting story because it was just a single stone that fell in somebody's garden. And as many of you know, the Nomenclature Committee has very strict guidelines about about naming of meteorites. And, you know, if I had just named it, if it had just fallen somewhere outside of the tribal lands and fallen near to the town of Ts'i'bikoh, which is close to where it fell, we would have just called it Ts'i'bikoh. But since it fell on the tribal lands, I suggested that the tribal council provide a name. And so they met and came up, and after multiple conversations back and forth, they came up with this quite long, unusual name for meteorite. So Dishchii'bikoh is the Apache name for the Apache ancestral name for the location which it fell, and Ts'i'lsŏݸsé Tsee means the star rock or star stone. But the formal name used in classification in papers is Dishchii'bikoh. And then I think here, yeah, so it's been reported to the Nomenclature Committee. And, you know, I also try to remind people when they submit stuff to the Nomenclature Committee that it's a peer-reviewed publication. So when people submit meteorites, you know, it's a publication that I cite. You can cite, because 12 people have reviewed your submission, and it's voted on. So these are 12 members, 12 meteoriticists from around the world, each with their different expertise, but they still vote on every single meteorite that gets submitted. And currently the NomCom is I was chair of the NomCom for a year or so. I was also the editor for several years, and it's an extremely busy society, committee, because they get on the order of several thousand meteorites submitted to them yearly for classified meteorites. But I still say to people, put effort into the submissions. You know, once it gets published in Meteoritical Bulletin, it's a publication that I will say to people, especially the students, that you can cite. So this is the meteorite. If people haven't seen the online Meteoritical Bulletin database, it's updated regularly. I think we're currently at, I don't know what, 65, 70,000 meteorites that are in the Meteoritical Bulletin. I think the numbers, in my opinion, are slightly skewed because the vast majority of those are from Antarctica. But there's the rules for Antarctica are that all the meteorites that get, since they're federally funded expeditions to go out there, every single meteorite that gets picked up has to be classified independently, even if it comes from an obvious same strewn field. So you could have one area that has several thousand, I don't know, L6 ordinary chondrites, but each one will be classified separately. Whereas the meteorites that get classified outside of Antarctica, which can be owned typically privately, people tend to focus on things that are interesting. I'm going to leave that word sort of as a vague. Interesting for collectors, interesting for scientists. So the vast majority of let's say, equilibrated ordinary chondrites from the deserts, vast majority don't get classified. I think I've recently thought about this, and there must be literally tons of ordinary chondrites from the deserts that are just sitting there unclassified and uncollected because really nobody has any interest in them. But anyway, this meteorite, Dishchii'bikoh, got accepted, got accepted as an LL7. That's a little bit of an unusual classification. Maybe LL6 would have been appropriate, but I think what I argued in this particular case that the almost complete lack of chondrules and equilibrated nature might be more, that the petrologic grade 7 might be more appropriate, but LL6 would have been appropriate as well. I'm only putting this up here as example. This is not to be read in great detail. This is just to give an idea of what a write-up looks like if you haven't seen one. And so and some areas of this can be very short. For instance, the history section on here is particularly long because this was a fall and there was a lot of information that went into the fall. For most North African meteorites, the history section is relatively short, and we'll just say something like, you know, so-and-so acquired a 50-gram stone from a meteorite dealer from North Africa or at the Tucson Gem and Mineral Show. And that's about all we know. But in this particular case, I thought it would be appropriate to put in some real detail in here for the future. And I really tried to encourage, especially for meteorite falls, because there's quite often, I would say that I'm going to just throw a number out there, 99% of meteorites that get put into the bulletin, that's the only time that information will be, probably the only time that meteorite will be studied in any great detail. So it's really, I think it's really important in this case to put some of this sort of detailed information. into the bulletin, because quite often they won't study. In fact, for other meteorites in the meteorite bulletin, quite often you'll come up with something. I'll say, I don't know, it'll say something like Winonaite, and it'll have the phthalate content, and it'll say, and that's about all the information. So how are you supposed to know if there's anything interesting about that particular, in this particular case of Winonaite, unless somebody puts that information into the write-up? So I really encourage people when they're classifying, put information into the write-up. What do you see? What does it look like? What does it look like in hand specimen? Is there anything unusual or not unusual in the petrography, for instance? And so in this particular case, it starts with history, and this is a very standard write-up for all the meteorites that get classified. So there's the history part, physical characteristics, petrography, in this case, geochemistry. And I think since this was done, we've also got the oxygen isotopes, which also overlap with the ordinary chondrites as well. And then finally, the classification, in this case, LL7, we saw some shock features, but we can talk about a bit more about that afterwards. And obviously, since we found them just after they fell, it's not weathered. And so this is just the first. This is just the first stab of what is this meteorite. The science hasn't been done yet. This was one of the papers that came out. This was in 2020, so a few years after the fall. It shows this was a real group effort to analyze this. One set of one person worked on the orbit of the stone. Other people worked on various types of isotopes, lead uranium lead dating. Other people worked on chromium isotopes. Other people worked on, so this whole team came together. This was quite an interesting. I thought this was a really fun group. This whole team came together to basically delve into at least a first sort of information. What is this meteorite? Where did it come from? Where did it derive? When, for instance, some of the isotopes gave us indication of when it broke off the main ordinary chondrite parent body, maybe the LL parent body. So all these things came together to tell us a story about this particular stone. And this, fortunately, this paper is available online for anyone who wishes to read it. So in the last few slides, I'm just going to put together some final thoughts. It's more about the science, which I could have gone into, but again, the paper's out there for anyone to read. So, I encourage people to go out there, download it, read it if they're interested. And then since when we came out with that paper, another group also came out with a paper. And it was interesting, if you looked at some of the comparisons about how big was the incoming asteroid and things like that, we have some differing estimations, because obviously we don't know exactly how big it was before it came into the Earth's atmosphere. But we're both within an order of magnitude about came up with the same sort of values. So Dishchii'bikoh, I say here, one of the interesting things that I always think is quite interesting here is that, I've seen various estimates of fall numbers, fall rates. I think one of my favorite order ballpark figures is one fall per square kilometer per 10,000 years, something on the order of I've seen that in print. I've also seen something on the order of, there should be on the order of 17,000 falls that reach the ground. So falls, so on the order of 17,000 per year, but we only pick up on the order of 10, a few more nowadays with Doppler, because of Doppler radar is really enhancing our recovery statistics. So that we should have more falls. I mean, Arizona should have a fall once every year or two. But we only have them once every few years. So Dishchii'bikoh was the first one in almost 60 or 70 years. And then after Dishchii'bikoh, we had in 2018 another fall. But what was really amazing about the Glendale fall, it was a single stone it fell in a valley. It was a relatively small event. It was the Meteoritical, the online database where people put their observations where they see a fireball. Only had a few recorded events, and I actually got a phone call. I got an email from somebody in, again, Northwest Valley, but about 40 minutes from me, he said I found a meteorite in my front garden. Now, normally I would ignore that sort of information because people say that all the time, and nobody had recorded a bright fireball or anything like that in the valley. So, he sent me a photograph, and sure enough, he had a really fresh fusion-crusted stone. Again, I still didn't believe him because it's relatively easy. Anybody can go online now and buy a meteorite and say they found it in their garden. So what I did, I went to one of my meteorite hunter friends and said, did we have an event in the valley? And he said, funny enough, he said 2 days ago, this was 2 days before this guy got to me, he said, we had a medium-sized fireball, but nobody's really investigating. I said, well, somebody's claiming to have found a meteorite in their garden. And so and fortunately this guy, so we had the event, so we knew a time signature, and he went and looked at went and downloaded the Doppler radar data for the Northwest Valley. Sure enough, there were in several sweeps, he saw a small cloud of material indicating that there were stones heading towards the ground. And we went back up to the Northwest Valley and searched, and I went onto the news, said to people, if you find black rocks in your garden, please let me know. I think you can all pretty much guess what happened then. I was inundated with photographs of black rocks from people's gardens in the Northwest Valley. But I think what I really learned from the Glendale fall was that not all meteorites fall with a giant sonic boom and dropping lots of stone. We can have something that's almost unrecorded dropping a stone. And this is probably why so few are found, even though we probably do have a fall or two or more per year just in the state of Arizona alone. Most of them just go unrecognized. And some of the things that everyone here on the group is I'm sure well attuned to. Each meteorite, why do we study them, as we tell the students? Each meteorite is bringing with it its own capsule of history, telling us about the solar system. And it's our job as meteoriticists to sort of unravel that, to look at that and put that into context. And I always like to say that each meteorite is like is a piece of a giant puzzle. I think about it, I don't know, a puzzle of 10,000 pieces, of which most of it is sky. And that's what each meteorite piece is. It's telling us, just giving us one more little bit of information. And a topic that I haven't talked about here, why do we study meteorites, is planetary defense. And I think that's a particularly important topic that should be covered in another talk. And also, just as out of fun, hunting for meteorites is super exciting. As I said at the beginning of the talk, we've had, 5 falls this year so far. The one in Oklahoma relatively recently, people are still searching for. Actually, I think I showed you, I have a slice of it here and several slices, and classifying that tomorrow. And the team that we got together to go out to look for meteorites here in Arizona, it was a great learning exercise for all. So we had grad students, myself, and some members of the public. So all of us really sort of came together to make it possible to hunt for, find, and for the meteorites. And in this particular case, this was the first time that we were able to gain access to tribal lands to search for meteorites. We've had several potential falls on tribal lands. There was almost certainly one a few years before Dishchii'bikoh up in the Navajo tribal lands to the north of us. Again, good visual observations of a fireball and even radar signatures. Again, this was before we managed to get access to the tribal lands here in Arizona. And even a few years before that, there was also an almost certain fall on the Tohono O'odham tribal lands to the south of us. And so the next time there's one on tribal lands, at least we know who to go to gain access, hopefully gain access to the tribal lands. And I have many people to thank. Obviously, pivotal was Jacob Moore here at ASU, Associate Vice President for Tribal Relations, and their then Chairman Ronnie Lupe of the White Mountain Apache tribe. He could have said no, but the two worked together and gave us access. Ranger Amos, who provided logistical support, and several other people here that I've just listed here. And I think I've got one more slide to have a look. Okay, I'll end it on this slide here. This one, it was a fun hiking out there, but it was also quite a tough place to search for meteorites. So why don't I finish there? I see we have several. There's several things in the chat here.
Okay, well, anyway, Laurence, let's all thank Laurence for giving us that fascinating talk about the nitty-gritty, the details of a meteorite fall and how to respond to it. I really appreciate it. So let's give him a sort of a muted applause for it. Appreciate it. Yes, as Laurence noted, there are a couple of questions already in the chat. And the first one that is pertinent can you use a drone with a good camera to do searches?
I mean, theoretically, but the stones in this area were so small. I mean, they were really the size of rabbit droppings. I have my stone here. I mean, that's it. I don't know if you can all see that. It's just a small, literally a black stone. So in this particular case, where a drone may be useful would be something like for the Texas fall right now, which is in relatively flat lands in southern Texas where you have a lot of open ground. In an area like that, it might be useful, but in this particular location, I think I don't see that it would be particularly useful. Literally, boots on the ground is the only way to go here.
Okay, and David wants to know how wide the area is.
The width of that Doppler radar signature was only about a mile wide, but about 10 miles long. So all the small stones were found in about a 1 square mile area or thereabouts, but the larger stones would have been further south, where we expect the larger stone or stones to be. But again, just the logistics of getting out there make it difficult. It is in an area where you could theoretically, hunt, but it would not be easy.
It seems to be a needle in the haystack.
Yeah. So as somebody says here, did the tribal council allow photography in designated areas? Yeah, it was interesting actually, because I know that we were very cognizant of there were things on the ground and things that you would want to photograph that normally people might have in other parts of the United States collected, but obviously we didn't collect anything that was of Native American origin here. It was one of the few areas that I've been to in Arizona that was, apart from that little dirt road, 100% pristine. There was no sign of anyone else having been there apart from in the past. So yeah, and I know speaking to Ranger Amos afterwards, once we left, they went out and what did they cleansed the area of our presence. I mean, we left nothing, but they cleansed the area of us being there. Were there any signs of weathering? We collected it before any major rains. There might have been a really light rainfall in this area. So in the stones that I collected, I didn't see when I cut them open I sliced them with alcohol. I didn't see any signs of weathering. Also, since they're LLs, there's relatively little free metal. So I suspect even it's been several years now, if we were to go out there now, the stones would look pretty much pristine.
Okay, anyone else have their hand up? Not yet. Well, anyway, I'll make a comment. I've seen, there's a beautiful SEM images that you have there, and it looks familiar to me. It looks very much like an annealed impact melt breccia. And you can see that there was melt, there were equilibrated clasts, that melt was floating around, and then the whole thing was annealed, wiping out the shock features and coarsening the grains in the glass and the liquid, the melt. So yeah, it's a beautiful looking rock. There's a number of rocks that have the impact melt breccias that have these recognizable barred olivine relics, like this one does, because they're the most easily discernible.
And what was really interesting, that cataclastic texture made working with the stones very difficult because it was so powdery. That's what made it was like it had been crushed, and I don't think it had anything to do with the impact, but it literally it's a very soft material. And also, I from one of your last papers, I went and looked for copper and found some nice areas with copper in it between the troilite and the metal, some nice copper grains.
Well, that's nice to hear. Well, we have another question here about this year's quote unquote secret fall.
I'm not saying anything.
Okay, well,
what part of the world did it happen? Not the United States.
Reading the question.
Yeah,
we will have to wait. Oh, but let me just ask you something about that. Can you give us an ETA roughly on when we will know something about it?
Oh, the secret one?
Yeah.
I mean, it's not in the United States. It's somewhere in Asia. I'll have to ask the meteorite dealer what state of it's being cut right now.
Okay, so maybe a few months we'll learn something
Yeah.
about it.
And by then it'll be long forgotten because there'll be another half dozen
I
balls.
see. Okay. Well,
We have a
Kevin has
hand.
something. Okay.
Hi. Yeah, thanks. This was really wonderful, Lawrence. I didn't even know half of what you were just talking about. It's great to learn. So I'll go be on a webinar with Avi Loeb next week. And he's advocating sending a ship to look for an underwater for this interstellar bolide that fell in 2014.
Of course he is.
And I'd like to bring some realism to this. One of the things that struck me is how important it is to have radar to get the trajectory. And I was just wondering if you could speak to how accurate or how precise the strewn field location would be if you didn't have radar data.
Yeah, the radar data is absolutely essential. Without, and we were lucky in this particular case because the weather conditions were perfect. The radar data and the fine location on the ground correlated absolutely. The Glendale one, it was off by about a mile, the radar, because we had upper level winds that shifted the stones. But so if we didn't, let's say just to give an example, let's say we were going to go hunt for the Glendale. Let's say we didn't have the Doppler radar and we hadn't had that first find, but we knew that there was a fireball. We would have had no idea where to look in the North Valley. It literally is looking for a small black rock in several square miles of ground. It would be virtually impossible. And it's really, there's been several things written on this recently. The Doppler radar has transformed the recent meteorite collecting from falls, and it's because it's allowed people to say, okay, instead of hunting in this 10 square mile area and never finding anything, we can hunt in this small area where we're likely to find something. So without Doppler radar, unless it lands in your house or something like that, it's virtually impossible, virtually zero. I mean, think about this. Look at Sutter's Mill is a perfect example. Sutter's Mill was 90 tiny stones weighing approximately 900 grams, and there's probably several thousand, I want to say human hours of hunting to find those 90 stones. So, and they knew where they were looking. They knew exactly where to look. So the chances of finding a small rock in the deep sea ooze after several years is zero.
It's zero, I know.
It's zero.
Yeah. Even if it existed, which the thing, according to Mark's Fries's models, it totally vaporized.
If it didn't vaporize, did it still have its extraterrestrial velocity when it hit the water?
Yeah, these are good questions.
Because if that's the case, then it would have, upon impact, if you've ever seen those videos of high bullets hitting water at high speeds, they just break apart.
Yeah.
So,
yeah.
But even then, again, I mean, the only time I've known where one was really collected in the water, you all remember the 600 kilo Chelyabinsk?
Oh, right.
But they knew exactly, because of the hole in the ice, they knew exactly where to go.
Yeah. Yeah.
That's right.
So I mean, I think that, it would be, I mean, can you imagine if we really had an interstellar meteorite? I mean, it would be super exciting.
Sure.
If anything could ever survive, that's the problem. Sutter's Mill was always surprised survived because it was, I think it was the highest velocity meteor to produce a fall. I think it's the highest ever. And it would have been a object this size, and imagine all we've got after all that hunting was 900 grams.
Yeah. I would love to talk to you this week about it, actually, Lawrence.
Okay.
So I'll catch up with you.
Okay, the real Kevin McKeegan has a question.
Okay.
The real Kevin McKeegan, please ask a question. Yes. Actually, I wanted to follow up on a comment that you made, and ask a little bit more about the radar data. I thought I heard you say that you expected that the large stones down trajectory would be about 4 kilograms.
Hmm.
And I was wondering what's involved in modeling that, because this thing broke up into many pieces, right? And you also commented that you expected to find these, 10-gram pieces or so, where you did find them. And so I'm just wondering what's involved in these models? How accurate are they? How well tested have they been, and so on?
Yeah, I mean, wonderful questions, but I can't answer any of them.
Okay.
No, that's the Mark Fries, and he should give a talk here because he could explain exactly. That's what he does. That's one of the things he does.
We should put him on the list, Alan.
Yeah, and his modeling's become what this area showed has become quite accurate now. With the input data that we had, and let me show. Oh no, I won't show it just now. But the modeling was very good at showing the breakup, where the breakups were, and then the Doppler radar showing the size ranges of the material. And so then that rainbow color sort of strewn field was based on that modeling. So all we had to go with the modeling so far was obviously the light, the sort of the low mass materials, which correlated where we expected the low mass materials to be. We have not yet proven the high mass materials because we haven't found them.
Right.
Okay, well, time is getting on. I want to thank Laurence once again for the interesting talk. I appreciate the level it was aimed at. And I want to remind everybody that we have a talk every month. And next month, on March 19th, we have a talk by Mike Zelensky at NASA Houston on do we already have a sample of Ceres? And so we'll all look forward to seeing if the answer to that question. In the meantime, I want to thank everybody. Kevin can stop recording. And thanks, everybody. Thank you, Laurence. And thank you.